Hi everybody. I'm sad I don't get to be with you today. But please send me your selfie from your table because it really does make me so happy to see them when I can't be with you in person. So remember to do that if you haven't done that yet. We're just going to talk a little bit about the Spring Year Round Lab data so that we can get you straight into working on worksheet 1, which is homework if you don't finish it. I think hopefully you should be able to finish it. That's my goal for you. And so I'm going to try to get through this quickly so that you have enough time to work on it and finish it in your groups. The only other thing is that on Monday, we're going to look at some spring break photos. So if you can make sure you email me yours if you haven't yet. We got some amazing submissions. So you want to join in on the fun. Okay, so we talked about this yesterday. We talked about this yesterday. All right, so how does amplitude affect the period? My guess is that when you graphed your data, you saw something that looks like this, which is real wonky. And that's because you needed to include the origin. So when you hit the settings button and you hit include the origin, all of a sudden the graph looks like this, which makes possibly, hopefully, more sense. So the way you want to figure out what kind of relationship this is you don't want to just put a curve fit on your graph. What you want to do is you want to look at the data and say, does this data fit the shape of the graphs that I know? So I know a quadratic graph, for example, looks like this. My data does not match a quadratic, so it's not a quadratic relationship. A square root graph looks like this. Now, it could maybe be a square root because it is flat, but at the top, but there would be more variance, especially considering we're doing a factor of 5 between our smallest and biggest data point. So because we took a pretty large range of data, we would see more of the square root shape if it was square root. Inverse. An inverse graph looks like this. And so this does not look like an inverse. It doesn't really look linear either because there isn't this like direct relationship of as amplitude gets bigger, so does period, or even a direct relationship of as amplitude gets bigger, period gets smaller. It doesn't look like that either. So in fact, the relationship that I'm seeing is that as amplitude gets bigger, there's like no change in period at all, right? There's no change in period. And so that indicates no relationship. This amplitude does not affect the period. All right, second experiment. How does mass affect the period? So we're going to do the same thing with our data, and basically this one's a little bit harder to see, but at the very end of your data, you should see a little bit of a flattening out. So it might look fairly linear, but then you should see kind of this flattening happening towards the end of your mass data. And so if it kind of looks linear with a little bit of a flat part at the end, that would indicate a square root relationship because we're seeing this like linear, but then it's kind of flattening out. So that indicates a square root. So how do we linearize a square root? It means that y is proportional to the square root of x, but we don't like to do square roots. So we do y squared versus x. We just square both sides of the proportionality. And so we're going to square t. We're going to square our y-axis, and then you should get a line. So we're going to use that now to write a physics equation. So we start with y equals mx plus b. On our y-axis is period squared, so that's big T squared. On our x-axis is mass, so we're going to substitute in m, standing for mass, not m for slope, for x. So I'm going to leave a blank for slope and a blank for y-intercept with my parentheses, because I always put parentheses around my slope and my y-intercept. Then I'm going to use units. So my slope units are going to be seconds squared, because we're doing t squared, so you square the units, over kilograms. And my y-intercept units are going to be seconds squared. Now, in our packet, we told you what this slope actually should be. Like, what is the theoretical slope? That basically means like, this is what your slope should be equal to if your spring is acting like a real spring. So that's 4 pi squared over k. So for number 7, we're going to use that theoretical value. But if you go searching for this equation on the green equation sheet, it doesn't exist. It's not there. What is there is the square root of both sides. So when we take the square root of both sides, you end up getting this equation. So the square root of 4 pi squared is 2 pi. The square root of m over k, and then the square root of t squared is t. They're the same equation. You can use either. So next, this question 8 is just asking you to apply proportional reasoning. So we want to determine the new period, so the factor of change of the period, if the amplitude is doubled. So I know amplitude doesn't affect the period of a spring. So it stays the same. The factor of change is 1. The period remains to be t. If I double the mass, I know mass does affect the period. And this relationship is a square root proportionality, where this is staying constant, so these are both going to be 1. This is becoming 2, and then this is staying constant, so this is 1. So that's 1 times the square root of 2 over 1, so the factor of change is square root of 2. For part C, same sort of logic, 1, 1, 2, so square root of 1 over 2. And then this, both mass and spring constant are changing. So 2 pi still doesn't change, but we get 4m over 3k. And so that's the square root of 4/3 times t. All right, let's talk, this is just kind of a summary. So amplitude has no effect on the period. Period and mass do have a relationship. And that relationship is mathematically reflected by this equation. Let's talk about energy. So energy is a review a little bit, but I want to make sure we know kind of where the spring mass system has potential energy, where does it have kinetic energy, and connect that to what we saw and observed in our lab yesterday. So the first question I want to ask is, why are there no lower quadrants for this graph? Why isn't there any negative y values? I hope you're thinking, because energy can't be negative. Energy is a scalar quantity. Energy doesn't care what direction things are. It's always positive because it's a scalar. It doesn't have direction. The only energy that can be negative is gravitational potential energy. All right, so next question. Why do I have a negative position quadrant? So the positions over here represent compression of the spring. So negative positions represent compressing the spring. This is equilibrium. So position 0 is when the mass is there. It's at equilibrium. And then positions over here is when it's stretching the spring. So we need the negatives to distinguish for the compression versus the stretching. All right, mechanical energy. The question you should ask yourself is there any work done? Because that would cause mechanical energy to change. There is no force acting on the spring mass system as long as it's on a frictionless table. And so therefore, total mechanical energy stays the same, no matter what position it's at. The spring potential energy is what we're concerned with in this situation. And when you pull the mass from equilibrium and stretch it, you let go. The mass is not moving, so all of that energy is stored as spring potential. At equilibrium, there is no stretch, and so therefore US equals 1/2 kx squared. There's no spring potential energy. When you fully compress it, there is spring potential energy again, and it's all spring. So our graph is going to look like this. It doesn't look like two lines, though. It's a curve because the slope of this graph, it's an energy versus distance graph. So the slope is the force, and we know the force, the linear restoring force, is a maximum here and is a minimum here. And so the slope should be steep when the position is big because the slope is the force of the spring. And then when the spring gets closer to equilibrium, there's less and less spring force, and so our slope is going to get smaller and smaller. All right, our kinetic energy graph, you can probably guess, is just going to fill in to show conservation of energy, but let's talk about why that makes sense. So kinetic energy is 0 here because it's not moving, right? You let go and it's not moving. It stops too when you do the oscillations, like it would stop for a second when it gets to maximum compression or maximum stretch. And then at equilibrium, it's moving really fast. So this also makes sense based on what we observed about our mass yesterday. All right, so now you're going to work on worksheet 1 in your groups. You hopefully will have enough time to finish it so that you have no homework. And I will see you all on Monday. I hope you have a great weekend. Please be diligent so that you don't have any homework. I really hope you don't have any homework this weekend. All right. Good luck working on it. We'll go over it on Monday.